Okay, so this next module is on energy bands and carriers. So the first two modules, this thing is, let's see. So the last module focused on how electrons are arranged in individual atoms. So the example that we ended off with in the last module was where you have a single nucleus. The single nucleus affects has a certain electrostatic potential boundary condition around it. If we were to just jump back here real quick. So the Schrodinger equation says that if you know what the electrostatic boundary condition is, the electrostatic potential, which is given by Coulomb's law, then from there you can figure out the solution to the Schrodinger equation, which is a set of wave functions which describes the locations of the electrons. So if you have the electrostatic boundary condition, you have the locations of the electrons. The locations of the electrons refers to the different energy states, the different orbitals. And for the case of a single atom, we saw that the solutions to the Schrodinger equation and the energy states of the electrons look something like this. You had these different orbitals, and we organized them according to the SPDF notation. We had the 1s orbital, 2s orbitals, 2p orbitals, and so on. Yes?
What's the Schrodinger equation of responsible for knowing? Do we have to actually work any of it out?
No, this is the thing. Since this is not a class in quantum mechanics, I don't expect you to be able to solve the Schrodinger equation. I want you to understand conceptually what it is. Yeah, so what goes into it, what you get out of it, and conceptually some of the basic ideas that the Schrodinger equation is a statement of total energy being the kinetic energy plus the potential energy. All right. So just to touch on last time, this was the solution to the Schrodinger equation for a single atom. This is where you have one nucleus, and there's no other nuclei around it. Okay. But as we find now, let's close this one. Silicon lattices, it doesn't just consist of one silicon atom, it consists of an entire lattice of them. Okay? And those silicon atoms are connected to each other. There's a very well-defined spacing between the atoms in the lattice. Okay? In this situation, the electrostatic boundary condition is very different. You have multiple nuclei. Each one of those nuclei gives off, has a positive charge, so it gives off an electric field, and therefore the electrostatic boundary condition is going to be quite different in the case of multiple atoms. So the solutions to the Schrodinger equation also look different. So that's what we're going to be talking about in this module. In the last module, we found out that the Schrodinger equation said that there are very discrete energy states. The 1s state, the 2s state, the 2p state. Okay, they're very discrete, and they had well-defined energy gaps between them. And that's one of the reasons why atoms will only emit light at certain wavelengths, as we saw at the beginning of Module 2. In this module, we're going to talk about when electrons are arranged in solids, meaning when there's multiple atoms, they form energy bands instead of discrete energy levels. An energy band is a whole bunch of energy levels that are very close to one another. And an electron can exist at any one of those states. We'll get into that. We'll talk about the mechanism of current flow, how to calculate carrier concentrations in semiconductors, and how to calculate electrical currents in semiconductors. So this module, from a practical standpoint, we learn how to make a semiconductor resistor. In order to make a resistor, we need to understand what carriers are, how carriers flow through the device, and that will ultimately allow us to calculate the resistivity of a semiconductor and the resistance of a semiconductor resistor. In the following modules, we'll get into diodes and transistors. So starting with covalently bonded silicon. Let's see. So over here on the right side, this is silicon. Silicon has 4 electrons on its outer shells. Okay, and the band structure, not the band structure, I'm sorry, the energy states for a single silicon atom, which is what we saw last time, were these. You had the 1s orbital, the 2s orbital, the 2p orbitals, 3s, 3p, and so on. Okay, we talked about how to fill up the electrons there. When silicon is bonded to 4 other silicon atoms around it, which you see here in the bottom right corner, right, this forms a tetrahedral binding that we talked about earlier. Now you have a different boundary condition, because instead of just one nuclei, you have this nuclei, you have this one, this one, this one, this one. So they all affect the solution to the Schrodinger equation. If we were to solve the Schrodinger equation, then we would see that the different energy states that we could get look something like this, where we have these things called hybrid orbitals. All right, the concept of hybridization, the definition of it, is that it's the alteration of orbitals due to covalent bonding. So let me draw this out. So one thing we're doing is we're literally changing the shape of the orbital. So if we take a single silicon atom, it looks something like this. The nucleus is in the middle, and this nucleus has a positive charge. Then we have this is the 1s orbital. We also have the 2s orbital. Then we have the 2p orbitals look something like this. Dumbbell-shaped ones. And the 3s and 3p start to overlap with some of those. All right, so these are where the electrons are supposed to be. An electron in the 2p z orbital will be in this region up here. An electron in the 2p orbital will be up in this region here, or it'll be in this region here. Okay, it's within that dumbbell-shaped region. Now, in the case of a silicon atom that's bonded with other silicon atoms around it, we talked about the fact that these electrons, they form covalent bonds with the other electrons around it. So each of these silicon atoms has 4 electrons around it. Okay, and these guys form covalent bonds. These two electrons will be shared between the neighboring atoms. So what the actual orbital looks like is they look something like this. They form these dumbbell-shaped patterns. So these are what the 1s, 2s, and 2p orbitals look like in single atoms. And then in a lattice, a silicon lattice, this is what they look like. This is referred to as an sp3 hybrid orbital. So that's what's basically showing here. Now where'd my mouse go? There it is. So when silicon binds to these other silicon atoms around it, it goes through its transitional state. We're not going to be looking at the details of that. But eventually it forms covalently bonded silicon in the diamond lattice. This happens very quickly. And instead of having the 3s, 3p, 3py, 3pz orbitals, these orbitals get changed into these sp3 format orbitals. Okay, these are called hybrid orbitals. So the coloring scheme here, basically showing so you have this silicon atom here. The green one is contributing one of the electrons here to this bond. This purple atom, this is contributing this electron. The blue one is contributing this one, and then the orange one is contributing this one. All right, so each one of these four neighboring silicon atoms are contributing one electron into each one of these covalent bonds. The sp3 hybrid orbital represents each one of the four covalent bonds. Okay, so the electrical state is different. The orbitals have different names, they have different energies. One other point I'd like to mention is that the electrons in the lower shell, these guys remain unchanged. Okay. In the single silicon atom, you have the 1s, 2s, and the 2p, x, y, and z. You still have the same thing in the covalently bonded silicon. What changed was the outer shell electrons, the ones in the third energy level. They became the hybrid ones. Oh, any questions on this? Now we can look at the band structure. So we're going to start talking now about energy band diagrams. Energy band diagrams describe all the states that the electron can be in. Okay, this is going to be a very fundamental component of this class. One of the things that you should be able to come out with at the end of this class is to be able to draw energy band diagrams, to be able to analyze them, interpret them, and so on. So this is the energy band diagram for a discrete silicon atom. This is what we ended off with in the last module. What we saw, there's the 1s orbital, the 2s orbital, the 2p. All right. This particular diagram is not showing the differences in energy properly. There's a large gap between the 1s and the 2s. There's only a small gap between the 2s and the 2p. All right. So this is not quite showing things to scale, but it does give you the idea that it illustrates the concept that these are different energy states. They occur at different energies. Electrons tend to fill up the lowest energy states first. The other concept we talked about is that the electrons can go from a lower energy state to a higher energy state if it's stimulated somehow. This is what a discrete silicon atom looks like. Notice that there are discrete energy states. They can either be here, or they can be here, they can be here, and so on. In the crystalline silicon, what's different is that you have multiple energy states. You have a whole bunch of energy states up here, you have a whole bunch of energy states down here, and then you have some, a region in the middle where there aren't as many energy states. And then the ones, the inner shell electrons, these energy states look similar to what you saw earlier with the discrete silicon atoms. Okay, this goes back to, going back to this slide, what changes, again, important point here, what changes is the outer shell energy states, not the inner shell ones. If you notice between these two diagrams, the 1s and the 2s orbitals, they're still at the 1s and 2s levels here. This part of the energy band diagram has not changed. What's changed is this portion of the diagram. Okay. In this region, you end up forming a whole bunch of energy states in a region, and we refer to these group of energy states as a valence band. And up here, we refer to this group of energy states as the conduction band. There's a whole bunch of energy states here. Within the middle there's a region where there are no energy states, and we call that region the band gap. This is a very important property of semiconductors. Probably the most visually descriptive application of the band gap is in LEDs. You've all seen light-emitting diodes. You notice light-emitting diodes emit different colors. So the color of the LED is actually determined by the band gap of the material. So if you want to get a red LED, you have to use gallium aluminum arsenide. If you want to get an ultraviolet LED, something that gives off ultraviolet light, you want to do gallium nitride. So you have to choose a certain type of semiconductor material that gives you a certain band gap, and that band gap will determine what color light the LED emits. The specific mechanics of that we'll get into later. But the band gap is a very important property of a semiconductor. Now, one of the questions that students tend to often ask is, these energy band diagrams look quite different. Okay, why are there so many energy states here? Why are there's we can count the number of energy states that we have in the discrete atom: 1, 2, 3, 4, 5, 6, 7, 8, and there are some more up here. But here we have what looks like an unlimited number of energy states. Each energy state we're just drawing with a dashed line here. So why is that? Does anyone know why we have many energy states? Why we have so many energy states? Yeah.
Is it possible it has to do with the hybrid orbital being formed?
It does have to do with the hybrid orbitals being formed, but there's actually a more basic reason.
Just proximity of all the other atoms.
The proximity of the atoms determines the arrangement of the bands. But why do we have so many energy states to begin with? The hint is this is one atom and this is crystalline silicon.
More atoms.
Yeah, more atoms, more electrons. Exactly. So the more atoms you have, obviously the more places you have for electrons to be, right? Right. So each one of these lines represents an orbital that's available in the silicon crystal. Right? So obviously the more atoms you have, the more orbitals you have, therefore the more energy states you have. This is a discrete silicon atom, one single atom. This is crystalline silicon, so there has to be a lot of energy states. What's interesting is how the energy states are arranged. And this gets to what we were just saying, that when the atoms are in close proximity to one another, these energy states actually cluster. They cluster into these bands. So this is called the conduction band. There's a region of energies. There's a whole bunch of energy states within this region. And there's a whole bunch of energy states within this region here, called the valence band. They cluster. Why does this happen? Well, if you solve the Schrodinger wave equation with that electrostatic boundary potential condition consisting of a silicon lattice, you take that three-dimensional structure and use the Schrodinger equation to figure out where the energy states are, the solution to the Schrodinger equation will give you where these energy states lie. Okay, so that all happens mathematically. I know it's hard to see unless you solve the Schrodinger equation yourself, but you can just take this leap of faith that this is what the band structure ends up looking like. If we were to solve the band structure for different atomic spacings, we'd end up getting a graph like this. This is always a graph that tends to be quite confusing for students, but we'll go over it. Could we maybe dim the lights just a little bit in the front? It might be difficult to see otherwise. Yeah, is that a little bit better? So we've seen up here the single silicon atom has just one atom, so it has a certain electrostatic potential condition. This is a single atom, and then here we have the lattice. Let me just draw this better. Each one of these guys is connected to three other ones. So I'm just drawing portions of the lattice. You get the idea here. I'm not drawing this. I'm not drawing this quite accurately here, but it's just to give you the idea that there are nuclei that are spread around like this. We've seen pictures of the diamond lattice in our notes, so we know what that looks like. And And this is the lattice. What was the point I was trying to make there? Ah, yes. The interatomic spacing, the spacing between the nuclei, we call this A, interatomic spacing. The interatomic spacing is obviously an important parameter in determining the electrostatic, the potential boundary condition. If we make that smaller, if we make that larger, that's going to change the boundary condition, and therefore it will change the solutions to the Schrodinger equation. This is what this plot here is showing. On the right side of the plot, okay, what you notice here, this says the relative spacing of the atoms up here at the top. Then here we see the relative energy of the electrons. So what we're doing is we're drawing energy band diagrams for different interatomic spacings. Let's just focus on one part of the diagram, and we'll get to this portion in a second. So when the relative spacing between the atoms is very large, the atoms don't affect one another. So this is the case all the way on the right-hand side of the graph. This is the case of discrete atoms. Okay, we have atoms that don't have any other atoms near it. The atomic spacing is very, very large. In this case, if we look just along this line, which I'm pointing out here, then we'll see that these are what the energy states are. We have the inner shell electrons here. This is the 1s. This is the 2s energy state. This is the 2p of here. And then we have the 3s and the 3p energy states up here. Oops. So that's for isolated atoms. As multiple atoms are brought, as the atoms are brought closer together, the wave function will change, and the energy levels become continuous energy bands rather than having these discrete states. So what we did was, at the right here, if we solve the Schrodinger equation, we'd get these discrete energy states that the electrons can be in. Now, when we bring the atoms closer together, when we bring a lattice of atoms closer together, we start to see that instead of having discrete energy states, they form regions where there's clusters of energy states. So for example, if we're here on the map, we would see that there's a region of energy states up here, a region of energy states down here. The energy states are shaded in green. Okay, instead of drawing a whole bunch of individual lines like this, there's no point in doing that. We just shade it green to show that these are energy bands. Right, as the atoms are brought closer together, the wave function changes, and the discrete energy levels become continuous energy bands with many energy states. So this is what these different energy bands look like. So if we want to draw the energy band diagram for a specific material, we can choose what, if we know what the interatomic spacing is, then we would just find one vertical line here along this graph, and then we would be able to see the distribution of energy states in the conduction band, and then we'd be able to see the distribution of energy states in the valence band here. So let's talk about silicon now. Silicon has a very well-known interatomic spacing, sort of, I believe, in somewhere in the 5 angstrom range. So silicon falls along this red vertical dashed line, or red and blue here. Okay, along this line here, this is where silicon falls. So what you can see here is that this diagram, of course, correlates to the same diagram I drew on the previous slide. Okay, the previous slide showed that there's a whole bunch of energy states in the conduction band, a whole bunch of energy states in the valence band, and there's a well-defined band gap, Eg, between them. For silicon, that band gap is about 1.12 electron volts. In these energy band diagrams, you have energy on the y-axis, and that energy is typically given in electron volts. 1 electron volt is 1.6 times 10 to the negative 19 joules. So this is the valence band, and this up here is the conduction band. This is the band gap in between them. Okay. So if we were to take the silicon atoms and we were to somehow, if we could magically increase the spacing between them slightly, then we'd be somewhere here on the map. So the band gap would actually get smaller. We'd still have a conduction band, a valence band, but the band gap would just become a little bit smaller. In fact, this is what happens. Let's say if we were to take germanium, for example, instead of silicon. With germanium, the interatomic spacing is a little bit smaller, and so you end up getting a smaller band gap. And in some cases, if we were here, if the interatomic spacing was in this region here, then we wouldn't have a band gap at all. If you don't have a band gap at all, you actually don't have a semiconductor. You have something that conducts all the time. We'll get into that in a second. All right. So is this chart making sense? Somewhat. Are there questions on this? Yes.
Well, this isn't a universal chart, or is it? Like this just covers a couple different types of atoms, or is this?
These are for elemental semiconductors. Okay. When you have one type of atom. If you have two different like compound semiconductors, the chart will change slightly.
Okay, but if it's single atom, this can be referred to.
Yes,
okay.
Yes. Depending on what the charge of the nuclei is, okay. This chart may change a little bit, but the general shape would remain the same. The general trends would remain the same.
And would it normally have an x-axis for distance or length?
Yes, the x-axis represents the interatomic spacing.
Would it normally have units on it though? Like if I was going to look at this, I wouldn't know where, you know.
Oh yes. This is a qualitative chart.
Okay.
But yeah, if you were to actually solve the Schrodinger equation, find out all the solutions, then you could put this on a log scale or some type of quantitative scale. So, but if we want to talk, quantitative scale, like right here, this dotted line represents about 5 angstroms.
Okay.
So this is the interatomic spacing for silicon. Right. So when researchers are trying to look at new semiconductor materials, they might, if they know what the interatomic spacing is, they can use the Schrodinger equation to predict what the band structure will look like. And so they could draw an energy band diagram like this. So for silicon, this is how you draw it. Turns out this diagram is extremely important in understanding what the semiconductor does, what its properties are. How does it conduct electricity? Is it able to absorb and detect light? How it behaves in a variety of situations all comes from the energy band diagram. So moving on to the mechanism of electrical current. All right, we've talked a little bit about energy states now. Now we're going to talk about how electrons move between energy states. At a very simple and conceptual level, electrical current is really just when an electron jumps from one empty state to the next one. Electricity is a movement of charge. And generally, the charge that moves are considered electrons. We'll talk about holes in a second, but right now let's look at electrons. So an electron is in one energy state here. The electron can hop between different energy states. Now, what does the electron like to hop between? Well, it will typically go to an equal energy state, something that has an equal amount of energy, or it might go to an energy state. If there's an available energy state with lower energy, the electron would like to hop into that. For example, if this was an energy band diagram, if there was an energy state down here, often the electron will like to occupy that energy state, right? Because electrons like to occupy the lowest energy state first. They can also move horizontally in energy states, meaning if you have other energy states with the same amount of energy, the electrons can hop between those. What the electron typically will not do is move to a higher energy state. It will not do that unless it is given some amount of energy. Right? That energy can come from multiple sources. It could come from just the temperature in the room. The only way to completely have no thermal energy is to bring down the temperature to absolute zero. That's what physicists often do in experiments. The other way you could stimulate an electron is by blasting it with light. Photons can energize the electron. That causes the electron to go up to higher energy states. This is the basis for solar cells, by the way. So in order for conduction to occur, the material must have an energy band containing carriers and empty states. So let's look at what this statement means. An electron can jump between these states, but in order to do that, there has to be some available states. If these states are full, obviously the electron won't be able to move into them. There has to be some empty states in order for conduction to occur. The inverse situation is also will not conduct electricity. Suppose you don't have any electrons at all. Then you have all these empty states, but you don't have any charges moving. Right, so the bottom line is, in order for conduction to occur, the energy band should contain carriers and it should contain empty states. In other words, it should be a partially filled band. We'll get into that in a second. Yes?
So is that why on the previous diagram you basically have a situation where it becomes very conductive to they're getting so close together that you're finding full states that have to be pushed beyond in order to reach a band gap?
Can you say that again?
When you go back to the previous diagram,
Yes.
it goes, they come closer together, they become fully conductive, and then it comes to a state where you have a band gap.
Mm-hmm.
Is that because it's gotten so dense once you pass that conductive zone that your states are essentially full and you need extra energy to reach a higher level?
Okay, I see where you're getting. There's actually a little bit more to this than just what the band structures are. This diagram here is showing us just where the energy states are. In order for conduction to occur, we also have to examine whether those energy states are full, whether they're empty, or whether they're partially full. So that's what we'll do next.
That's what I mean.
So in order for the material to be conductive, if we go to this band diagram, this conduction band can be full of electrons or it could be empty. And let's go to the valence band. If the valence band is completely full, for example, it won't conduct electricity. If one of the bands is completely empty, for example, if the conduction band is completely empty, that won't conduct electricity. But if either of these bands are partially filled, they're not 100% full, they're not 0% full, then they will conduct electricity. This will make sense once we start talking about the Fermi function. So we'll get into this question in just a second. The question is, how does this energy band structure relate to how conductive a material is? That's ultimately what we want to answer in this by the end of this module. And there's a few more concepts we have to cover before that. So this is the energy band structure for crystalline silicon that we saw a few slides earlier. We have the conduction band, a whole bunch of energy states clustered around here, and a whole bunch of energy states clustered around here. This is the valence band. And then we have the band gap in the middle. There are no energy states in the band gap. Now, if we compare this with a single crystal silicon, one of the things we notice is there are a bunch of energy states like this, and they're very close in energy. So what that means is that the electron can actually jump between one state here, and it can go between this state and another one that's very close to it in energy. An electron here will not jump to an energy state here unless it's given some form of energy, unless it's given some form of stimulation. By contrast, an electron that's sitting here can jump to an energy state just a little bit above it or below it without any additional energy. So the fact that you have bands makes it easier for electrons to travel from one state to the next, because these energy states are so close together in energy. It makes it easier. So you have to have energy bands in order for material to be able to conduct electricity. Discrete atoms don't conduct electricity, right? If you just have a noble gas, for example, that's not really conductive. So this slide just talks about a shorthand for energy band diagrams. like I said, we don't want to have to draw out all these energy states like this every time we want to draw an energy band diagram. We like to have a shorthand. So the shorthand looks something like this. The conduction band, where most of the interesting stuff in semiconductors happens right here, in between the conduction band and the valence band. So what we do is we draw a line that represents the edge of the conduction band. Okay, so this line EC lines up with the beginning of the conduction band here. We draw another line EV, which lines up with the top of the valence band here. Okay, so this represents this area represents the conduction band. This area represents the valence band. However, another important point is that we don't actually draw. We don't even bother shading in these areas, because again, that would take time. We just draw basically these two lines, EC and EV, to represent the top of the valence band and the bottom of the conduction band. This region here is the band gap. So a lot of interesting stuff happens just in this part of the energy band diagram. So this consists of a whole bunch of energy states that are clustered together. Same thing up here. This is the band gap. Sometimes we label the band gap in there as well. And notice that we don't even bother drawing in the inner electrons here. The reason we don't do that is because usually those inner electrons don't really participate in any of the electrical conduction ability of this material. Basically, we don't care, so we don't bother drawing them. It saves us time. All right, so we took this complex energy state diagram and we just condensed it down into something that we can draw easily. All right, now let's start thinking a little bit more about energy band diagrams. This slide shows the energy bands diagrams of insulators, semiconductors, and metals. So we have an insulator here on the left, we have a semiconductor here in the middle, and we have a metal here on the right. So the features that we want to point out here. An insulating material may have multiple energy bands, right? Because in insulator, it's not a single atom. It's a, insulators are also like they're groups of atoms packed together. Any solid material is obviously more than one atom. So they form bands. The difference between an insulator and a semiconductor is that the spacing between the bands is larger for an insulator. So the insulator typically has one band which is completely filled, another band which is completely empty. So let's go over the insulator. Will this material conduct? We know that insulators don't conduct electricity, but why? How does the energy band diagram tell you that?
It takes a lot of energy to jump that band.
Yeah, let's suppose the electron is not jumping this band. It's not going from this energy state to here. Let's just look at one of the bands individually, one at a time. What happens if you have an empty band? There's no conduction. This band will not conduct electricity because it has no carriers. Right? This band down here also will not conduct electricity because it has a whole bunch of carriers, but those carriers don't have room to move. All the energy states are full. Remember that normally an electron will move to another energy state within the same band. Right? So this one's already full. There's no movement happening here, and here you have no charge at all. So in this case, the insulator generally does not conduct electricity. Now keep in mind that a semiconductor looks the same thing as an insulator, except it has a smaller band gap. The difference between the semiconductor and the insulator is that if the semiconductor is placed at room temperature, or some temperature above absolute zero, this energy gap is small enough that an electron could jump from this band into this band. If that happened, what would happen? If that happened, how would that create conduction?
There will be partially filled gap size of conduction. Okay.
Exactly. Both bands now are partially filled. You know, if an electron moved from here to here, then this would be mostly empty, but it would have like maybe a few electrons up there, right? So this band becomes conductive. The valence band would be almost, you know, be 99.9% full, but it would still have like a few empty states there. So, and those empty states help the electrons move back and forth. So in the case of a semiconductor, the way that is drawn here, this material is not conductive. But if you were to increase the temperature slightly enough for an electron to jump up to this energy state here, then the material becomes conductive. All right. So that being said, if we look back at the insulator now, if you were to supply enough energy to the electrons of an insulator, theoretically you should be able to get it to conduct electricity as well. The problem is a lot of insulating materials will probably melt before you do that. Right. Like, you know, rubber, material like rubber will probably melt before you get to the point where there's enough energy for these electrons to exceed the band gap. Silicon is the most common semiconductor material. It has a band gap of about 1.12 electron volts. There are other materials that have a band gap a little bit smaller than that, maybe half of that. Diamond, it can be used as a semiconductor, but it's generally an insulating material. Remember, diamond has the same structure as silicon. Carbon is a column 4 element, just like silicon is. But it's a smaller element. There's a different interatomic spacing. The band structure is very different for diamond than it is for silicon. Diamond has a band gap of, I believe, somewhere around 4 electron volts, 4 times larger than silicon. So it's much more difficult to get diamond to conduct electricity than it is to get silicon to conduct electricity. So in both these cases, you can see the differences. Now, in the case of a metal, the metal has what's called overlapping bands. Right? They may have band structures. They may have a band structure that overlaps with another band structure here. So what that does, it creates a single band, right? Because these bands are connected together, and that band is partially filled, right? Even at zero temperature, even at absolute zero, this band is partially filled. So these types of materials will conduct electricity at any temperature. Another example is if we have a material that has a partially filled band for other reasons. Okay, so this particular example, we could say that this upper band conducts electricity. It's partially filled. It's an overlapping band. This is partially filled also, so it conducts electricity. And in this case, this band is completely filled, so this one does not. So this band and this band are responsible for conduction in this material. This band does not contribute. This is an example of just an arbitrary diagram. Okay, this is not trying to name any specific metals. Okay, different metals will have different band structures, but the defining feature is that they will have a partially filled band somewhere, which allows it to conduct electricity. So getting to electrons and holes now. So from the band diagram before, we can see that semiconductors act as insulators at 0 Kelvin. And at elevated temperatures, the electrons get excited and jump into EC, the conduction band. This results in an electron-hole pair being formed, which results in an electron in the conduction band and a hole in the valence band. All right, so how we would denote this in an energy band diagram is that we can draw EC, we can draw EV. Now, under normal circumstances in a semiconductor, as you see from this diagram, the valence band is mostly full of electrons. The conduction band is empty. Now, what does this physically mean? One important thing that I want you to come away with in this class is the ability to understand the meaning behind the energy band diagrams. How does the energy band diagram correlate to actually what is specifically happening in the semiconductor? We'll talk about that in just a second. Just a quick definition is that an electron in the valence band is participating in a covalent bond. An electron in the conduction band is free from that bond, so it's free to move about the lattice. We'll get into that in a second, but let's just assume that the valence band is filled with electrons. Okay. In the future, when I draw the energy band diagrams, I'm not going to bother writing out all these electrons, but for the time being, I'm just putting them here just so you understand that the valence band is mostly full. Electrons will go to a higher energy state if they've been stimulated by some form, whether it's light or temperature. Those are the most common ones. If an electron acquires enough energy, so in other words, if it absorbs energy larger than the band gap, then the electron can go up here. And so what will happen there is that this leaves you with an electron up in the conduction band, and it leaves you with an empty state in the valence band. Okay, so we refer to this as just electron, and we refer to this guy, the empty state there, we call that a hole. So remember at the first lecture I said there's two types of charge carriers in semiconductors. There's an electron, which has a net negative charge, and we have a hole, which has a net positive charge. Okay. Why would a hole have a positive charge?
It's a missing electron.
It's a missing electron. Exactly. Exactly. So what this physically means, let's call this electrons and holes. So this is what it looks like in terms of the energy band diagram. Now, physically, in the physical model, we can think about it like this. Let's say we have silicon atom, silicon atom. I'm only drawing 5 of them. Obviously, you know that there are more. Covalent bond between them. All right. Now, this covalent bond consists of 2 electrons, right? This one on the right here. Suppose this one of these electrons. Let me redraw this in a way that's a little bit easier to understand. So, just draw out the electrons here like this. These are the covalent bonds. Now, if this electron obtains enough energy, if you remember from chemistry, an electron, if it obtains enough energy, it can be broken away from this bond. All right, when that happens, now you have we have a free electron here, which has a net negative charge. And then we have an incomplete bond. This incomplete bond is called a hole. Now, since this incomplete bond has one less electron than it should be, it has a net positive charge. So we'll just denote this H+. This whole thing is considered a hole. An incomplete bond is considered a hole. So this is what it looks like in terms of the energy band diagram. This is what it looks like in terms of the physical model. Now, if we want to do a shorthand here, we won't bother drawing out all these electrons here. We will just say that there's an electron here, and we'll say that there's a hole here. You see how that just makes it easier to draw the diagram. But physically, this is what's happening. Now this electron here, once it is free from the bond, the electron can sort of move about the lattice. So this is one way that the electron can conduct electricity. The electron jumps between different energy states within the atom. For example, let's say there happened to be another empty energy state next to it. The electron could come down here like this. Now, the way that would be represented in the energy band diagram is that the electron comes back down to the valence band. Valence band means that the electron is participating in a covalent bond. So the electron moving from here to here would be represented by this movement in the energy band diagram. That's called recombination. The electron can also move about the lattice, remaining in its higher energy state where it's not particularly bound in a covalent bond, but it's just loosely bound to the lattice and it jumps around. That refers to an electron moving about the conduction band, moving about different states in the conduction band. All right, so now let's talk about holes now. These electrons can, of course, move around, but the holes could move around too. Let's say that the hole went something like this. Let's say this incomplete bond just transferred over here. So this electron moved this way. It completed the bond here. So what would happen then? Sorry. So let's say one of the electrons moved from here to here. This bond then becomes complete, and now this bond becomes incomplete. So this becomes a hole. So when these electrons are shifting around, that actually causes the holes to move as well. Right? So a hole can move around the lattice similarly to how an electron can move about the lattice. One difference, though, is that the holes tend to move slower. Incomplete bonds tend to move slower through the lattice than electrons do. They're less mobile. So, and the term that semiconductor people use is they say the electrons have higher mobility than holes do. All right. So let's just finish up this slide, and then we'll take a break. So from the band diagram before, we can see that semiconductors act as insulators at 0 degrees Kelvin. At elevated temperatures, the electrons get excited and jump to the conduction band, EC. This results in an electron-hole pair. So the electron moved from here up to here, and it left a hole, an empty state in the valence band. So now we can conduct electricity because, as many of you said, now the two bands are partially filled. Conduction band can conduct electricity, the valence band can as well. One misperception that students always have in the class is they say, like, well, only the conduction band can conduct electricity. That's why it's called the conduction band. That's not correct. Okay, the valence band can conduct electricity, so can the conduction band. The distinguishing factor is this: is that the conduction band, the type of carrier is the electron. Electrons moving about the conduction band is one way to conduct electricity. In the valence band, the charge carrier is referred to as a hole. These holes, this hole can move about the lattice, right? When an incomplete bond moves from one place to another, that represents a hole moving from one energy state to another within the valence band. So those are your two types of charge carriers. The same phenomena will not occur with an insulator because the energy band gap is very large. So it would take a lot of energy to get the electrons to go from one band to the other. Okay. So let's stop there. Let's just take a few minute break. So continuing our discussion then about, we're getting into intrinsic semiconductors now. There are intrinsic semiconductors, and then there are extrinsic semiconductors. Extrinsic semiconductors occur when there's a process called doping, where we put impurities into the silicon crystal. We'll talk about that in just a second. But before we talk about that, we should talk about what a perfect semiconductor crystal is. This is something that has no defects, no impurities or dopants added to it. The structure of a silicon lattice, I've drawn that many times for you right now. This is a picture from the book. So we have silicon atoms, and those silicon atoms are connected by these bonds. Now, the book denotes these by 2 lines here. Okay? And those 2 lines represent a covalent bond between the adjacent silicon atoms. Now, you have electrons. So these electrons are, these electrons are the ones that are free to jump about the lattice. So this would be an electron that's in the conduction band. And then you have these holes, which are incomplete bonds. Okay, and these incomplete bonds can also move around the lattice. Now, your initial thought might be, well, if you have, in perfect silicon, if there's no defects, if you're at room temperature, would you have electrons and holes? And the answer is, as we said before, you don't have any electrons or holes if you're at absolute 0. But if you have enough temperature, even at room temperature, there's enough energy for an electron to break away from this covalent bond. So that creates the electron here, and it creates a hole, otherwise referred to as an empty state, or incomplete bond over here. All right, since the electrons and holes are created in pairs, the concentration of both are equal to each other. So at room temperature, the number of holes, n, is equal to the number of, the number of electrons, n, is equal to the number of holes, p, and that's equal to a constant, and that constant we call Ni. Okay, let me also write this down. 1.45 times, for some reason times 10 to the power of 10 per centimeter cubed. All right, I'll write it here. Ni for silicon is equal to 1.5 times 10 to the power of 10 per centimeter cubed. This is the intrinsic carrier concentration. This means that if we were to take a 1 centimeter cubed of material, 1 centimeter cubed of silicon, and we were to count up all the electrons within here and all the holes within here, the number of electrons would equal to the number of holes, and that would be about 1.5 times 10 to the power of 10 electrons or holes. Okay, they're created in pairs, so the number of them are equal. That's a lot. I mean, that's, it's quite a bit. So, questions for discussion. If we were to elevate the temperature, would Ni increase or decrease? Why would it increase, Mike?
You give more energy to the electrons, so they can move around.
Exactly. If we were to increase the temperature, there's more electrons. If we increase the temperature, more electrons can jump from the valence to the conduction band. So therefore, you're going to get more electrons. You're also going to get more holes. They're created in pairs. So at higher temperatures, Ni will increase. There's actually an exponential dependence on temperature. Second thing, recall that at a non-zero temperature, electron-hole pairs are constantly being created. Why isn't the carrier concentration constantly increasing? So let me rephrase this question. Okay, suppose we're at room temperature, right? Electrons are jumping into the conduction band. So if this process continues forever, eventually there should be no electrons left in the valence band, right? We're going to deplete all the electrons in the valence band. So why doesn't that happen? Because what?
They also recombine with holes.
They also recombine. That's exactly correct. The reverse process also happens. Turns out that when an electron goes from the valence to the conduction band, it stays up there for some time, and then it eventually comes back down. And this process happens constantly. Electrons go up and then come back down. And the generation rate, at equilibrium, the generation rate is equal to the recombination rate. So because electrons are being generated and they're also recombining, the two processes are in equilibrium with one another. That's why the carrier concentration isn't changing. It reaches an equilibrium state. So intrinsic carrier concentration versus temperature. As we said, when you go to higher temperatures, we can expect that the carrier concentration the intrinsic carrier concentration will increase. This plot shows this phenomena for three different very common semiconductor materials. Silicon is here in the middle here. That's this line here. Germanium is another popular column 4 element. It's right below silicon on the periodic table. Also column 4 forms tetrahedral bonding, but the atom has a different size. And then here we have gallium arsenide. This is a popular compound semiconductor material that's used in LEDs. They're used in light detectors. They're used in lasers and so on. And this is a compound semiconductor. It appears here on the map. So one more thing I want to point out is that if we look at the x-axis, which is shown up here, it might be a little bit hard to see, but this says 500 over here, 400 over here, 300, 200. So it's actually the temperature is decreasing as we go from left to right. So don't let this graph confuse you. All right, what's being plotted here is 1,000 divided by the temperature. Okay, it's not temperature on a linear scale. It's 1,000 divided by the temperature. All right, so the left side of the plot is going to have the higher temperatures. The right side has lower temperatures. What you can see, what's in common for all three of these materials is that you can see that the intrinsic carrier concentration increases as we go from low temperature to high temperature, as we go from 250 to about 500. What you also notice, here's the value that I talked about here, 1.5 times 10 to the 10. That's the intrinsic carrier concentration for silicon at room temperature. Room temperature is about 300 Kelvin. Right? The conversion between Kelvin and Celsius is about 273 degrees. Okay, if you take your Celsius in temperature and you add 273 degrees to it, you'll get the temperature in Kelvin. So 300 Kelvin is about room temperature. So what you notice about the difference of these materials, the germanium has a higher intrinsic carrier concentration than silicon. Silicon has a higher intrinsic carrier concentration than gallium arsenide. What could you say about the band gap of these materials? Which one has the largest band gap, do you think? Gallium arsenide? I heard gallium arsenide. Why does gallium arsenide have the largest band gap?
Because looking at the ion concentration, it has the lowest at every point at every temperature.
At every temperature, exactly. At every temperature, the intrinsic carrier concentration is lower. In general, the intrinsic carrier concentration is just lower for gallium arsenide versus silicon. And indeed, gallium arsenide has a larger band gap than silicon. I can't remember what it is off the top of my head right now. Silicon is about 1.12 electron volts. Gallium arsenide is higher than that. And then the opposite would also be true. Germanium has a smaller band gap. It has a higher intrinsic carrier concentration. So the logic is this, is that, the larger the band gap is, the more energy it takes to get an electron up from the valence to the conduction band. So there's going to be fewer carriers the larger the band gap is. Gallium arsenide has a larger band gap, so it has lower intrinsic carrier concentration. Germanium has the smallest band gap. I think it's somewhere around 0.6 electron volts, and so that has the largest carrier concentration. Notice that the carrier concentration here is on a logarithmic scale. Okay, this is 10 to the 6th, 10 to the 8th, 10 to the 10th, 12, 14, 16. Yes?
How does the ratio of the band gaps between gallium and silicon relate to the ratio of their unit cell structure?
The ratio of their unit cell structure?
Yeah.
You mean the ratio, like how, the interatomic spacing, you mean?
Yeah.
I don't think there's a specific mathematical or simple mathematical relation for that. You have to solve the Schrodinger equation. However, there is an equation describing the carrier concentration versus the band gap. Okay, and I'll be giving that equation later on. Right, there's an exponential dependence on the band gap.
Will it also relate to the size? Because if you look at silicon and germanium, they are all in the same period, right, on the periodic table. But as you go down, their sizes increase, and then the attraction by the nucleus to the outer shells begin to decrease.
Mm-hmm.
So if there isn't so much attraction between the valence electrons and the nucleus, then that means that they are easily available for transfer or to jump into different energy bands. That's what I think is the reason for the germanium being more, able to produce more electrons than silicon. Since silicon is smaller than germanium, the force of attraction between the alpha electrons are very small.
We're not talking about the
Reaction.
we're not talking about the ability to produce electrons. Remember, we're just talking about the band structure. If the band gap is smaller, then there's going to be more electrons generated. Now, if we look back to this graph here, you recall this one. Silicon is here on the map, okay? So if we were to increase the atomic spacing, okay, so we're moving this way, right? This is the relative spacing between atoms. Germanium is below silicon on the periodic table, so it has a larger atomic spacing. So we're moving from here to about here. Notice that the band gap is smaller. These are the solutions to the Schrodinger equation. The band gap is smaller as we move to the right, as we increase the interatomic spacing. If we go the other way, if we go to one up on the periodic table, right above silicon is carbon, right? And crystalline carbon is diamond. Diamond also exhibits this type of band gap structure, except as you can imagine, the band gap is much larger. Yeah, the gap between this upper band and the lower band is much larger for diamond. So diamond would have a very low intrinsic carrier concentration. So now that we've talked about intrinsic, let's talk now about extrinsic, doped semiconductors. All right, intrinsic semiconductors on their own have some interesting properties and they have some uses, but most of the time when we deal with semiconductor devices, engineered semiconductor devices, we are dealing with doped semiconductor devices. Okay. One way to generate carriers in semiconductors is by introducing impurities into the crystal structure, in other words, by doping them. Doping involves adding column 5 elements or column 3 elements when forming the silicon crystal. Now, we'll get to this in a second. The reason that we want to dope is that we make the semiconductor material more conductive. Okay. On its own, silicon is not a very conductive material. Okay. It has a relatively low conductivity. The cool thing about silicon is that we can make the material 10 times more conductive, 100 times more conductive, 10 to the 4th, 10 to the 5th times more conductive by adding dopants into the lattice structure. Okay, and most often this is what we do when we're making semiconductor devices. All right, so when we're doping, this is what doping looks like. Oops. An ordinary silicon structure would look something like this. All right, we've seen this many times now. I'm drawing a 2D version of this. You know what the actual crystal structure looks like. But let's say I replaced this silicon. I replaced that with phosphorus, let's say. Okay, phosphorus is a column 5 element. So if we look here, examples of dopant atoms. If we want to dope a semiconductor N-type, an example of that would be phosphorus. You could also do arsenic. You could also do Sb. What would happen if we replaced a silicon atom with phosphorus? So a silicon atom looks something like this. 1, 2, 3, 4. Phosphorus looks something like this. 1, 2, 3, 4, 5. We have an extra electron, right? So what happens to the extra electron when we put this into the lattice?
Conduction band.
Yeah, you have, well, physically, yeah. We'll talk about the conduction band in a second, but physically you can think about what's happening is that we have this extra electron, right, that's not participating in any of the bonds. So this extra electron is free to hop about the lattice. Okay, so from an intuitive standpoint, that's pretty much what's happening when we incorporate a phosphorus atom in there, a column 5 atom. All right, let's delete this for a second. Go back to silicon. Now let's do the opposite. Let's say, so this is a column 5 element. So this is N-type. This is an N-type dopant. Now we also have the option of using column 3 element, which is called a P-type dopant. Column 3 atom would be something like boron. And boron has 3 electrons in its outer shell. So if we replace the silicon atom with boron, what would happen? You have a hole, right? You have one. If this electron is missing, that means you have an incomplete bond here, right? Where the silicon atom has provided one, but the boron atom didn't provide anything. So this represents a positive hole. And this positive hole can also shift about the lattice, as we said before. They can move about. So this is an easy way of introducing electrons and holes into the lattice. Notice that there's a 1-to-1 relationship. For every boron atom that we put in there, you can think about as one hole being created. For every phosphorus atom that we put in there, we create one electron. Typically what we'll do is we'll dope with one type or the other. So if we want to get N-type, an N-type semiconductor is a semiconductor that has electrons. Okay, it has more electrons than holes. That's N-type. We dope with the column 5 element. If we want to get a semiconductor that has more holes than electrons, then we dope with column 3. If we were to have an N-type semiconductor, which band is responsible for conduction? In an N-type semiconductor? The conduction band. Right. So for an N-type semiconductor, we're creating electrons in the conduction band. For a P-type semiconductor, we're doing the opposite. We're creating holes in the valence band. And the valence band is the one that's responsible for conducting electricity. So the type of dopant, we have N-type. N-type increases electron concentration in the conduction band. Acceptors, P-type dopants, column 3 elements, they increase hole concentration in the valence band. A boron is a very common column 3 or P-type dopant. Other examples are aluminum, gallium, and indium. So how does doping change carrier concentration? So we talked about it in terms of what's happening in the physical model. Let's now talk about what's happening in the energy band model. So recall that that the perfect silicon crystal has a band gap where there are no energy states. We've drawn that a few times before. And now what happens, if we're adding a dopant, we're introducing energy states within the band gap. So donors introduce an energy level near the conduction band which is occupied by electrons. These electrons can easily jump into the conduction band at temperatures of 50 to 100 K. So if we look at the donors real quick here. All right. Now remember, adding a foreign atom into a lattice, it upsets the band structure. Right? If you have to solve the Schrodinger equation again, and the Schrodinger equation will give you a different band structure. Now, what ultimately ends up happening is that if you introduce a dopant atom, the dopant atom introduces an energy state at an energy near the conduction band, but not quite at the conduction band, but very close to it. All right, so in this diagram here, when I drew out the fact that you had this extra phosphorus atom. That extra phosphorus atom is introduced into the lattice. If you are at 0 Kelvin, those electrons will actually remain at that extra energy state induced by the column 5 atom. Okay, so a subtle point here: if you dope a semiconductor N-type, but you're at absolute 0, it should look the same as a non-doped semiconductor. It should look the same as an intrinsic semiconductor, at least in terms of its conductivity. But the difference is that these electrons can easily go into the conduction band. So the electron going into the conduction band means that that electron is free to move about the lattice. So these electrons can, even at 50 Kelvin, which is, like 200 degrees below 0, still enough energy for these electrons to get into the conduction band. That means that the electrons are free to move about the lattice. So when they do go into the conduction band, that's when they can conduct electricity. Acceptors do something very similar, the analogous thing. They end up creating holes. Now, acceptors introduce an unoccupied energy levels near the valence band. And the electrons can then jump into these levels at 50 or 100 K. So let's zoom in on this here. So the boron atom, since I have the boron atom drawn out here, you can easily see this. The boron atom is introducing an incomplete bond, right? Because it has one less electron than the neighboring silicon atoms. So that is represented by the fact that you have an energy state, but that energy state is empty. That energy state occurs at an energy just slightly above the valence band. At even low temperatures of 50 K, again, at 0 K, the acceptor, the conductivity of a p-type semiconductor should be no different than an intrinsic. But even at small temperatures, that's enough for the electrons to gain an energy to go into this, to the acceptor level. Okay, and that leaves behind empty states. That leaves behind holes in the valence band. These white circles are called holes. All right, and sort of physically what that means is that you're creating this empty state. Okay, that's the hole, and these holes are free to move about the lattice. Okay, there are some subtle differences that we're not quite going into here that has to do with the values of what the energy states are. But for the purposes of this class, this is a good model for understanding doping. Let's do one more slide here, and then we'll finish up. So how doping changes the carrier concentration, we've sort of drawn this already, so we won't spend much time on this. Column 5 element has 5 electrons in its outer shell. When it bonds to the silicon lattice, it has an extra electron, and that extra electron is free to move. Only a small amount of thermal energy is needed to free it. Okay, it's loosely bound to the lattice. So the electron is essentially free to move about the lattice, conducting electricity. In the case of a column 3 element, 3 electrons in the outer shell. So it can only complete 3 out of 4 of the necessary bonds with the neighboring atoms. With only a small amount of thermal energy, the incomplete bond can move from place to place within the lattice because the neighboring electrons can hop into the incomplete bond. Okay, we've already talked about this, but I'll just mention it one more time because sometimes students are confused about this. This here is an incomplete bond. If an electron here This is a complete bond, so this consists of 2 electrons. So if an electron decides to move over here, then what that will do is that will make this bond incomplete. It will complete this one, right? So you'll end up with a complete bond here, incomplete bond here. So your hole is essentially moved from here to here. So that's how the holes move about the lattice. Okay. So this is what these are what doped semiconductors are all about. They change the conductivity of the material. We'll talk about other ways that you can change the conductivity of the material, and next time we'll get into actually calculating the carrier concentrations.